merge procedure. So what was the responsibility of this merge procedure? So it used to take two arrays, array 1, array 2 of sizes m and n, correct? And both of them must be sorted initially. And then the output of this was a sorted array of size m plus n. So the merge procedure should merge all the elements of this and this such that they appear in a sorted way. The only important requirement is that both of them should be individually sorted initially. Okay. What was the time complexity over here? M plus n. And what was the space complexity? It was also m plus n. Could you do it in m plus n time without using extra space? Was it possible to do in order m plus n time without extra space? So apparently it wasn't, right? Why? Because I need that extra location where those m plus n things are to be accommodated, because this array cannot be made of size m plus n, this array cannot be made of size m plus n. And also if you try something like trying to place m smaller elements over here and n larger elements over here, you will see that your time complexity will increase, okay? It will not be m plus n. So that was the catch over here. Now let us think one very simple thing, that if I have to do the same thing with linked lists. So let's say there is a linked list like 1, 5, 5, 9, 15, 23. And then I have second one like 3, 4, 4, 17, 19. Let's say these two linked lists I have, and I have to merge them. So both of them are sorted, individually both of them are sorted, and I am supposed to create an output linked list which should contain all the nodes, and they should also come in sorted order. Can I solve it exactly how I did for simple arrays? Yeah, so how I merged two simple arrays, don't you think I can merge two linked lists also in that manner? I think I can do that, right? So that should be very easy to be done. So what I can do is that, again, I have got two pointers and I'm going to call them head 1 and head 2. And both of them are moving in positive direction. Now the moment I see that head 1 is smaller than head 2, one thing is for sure, that at any point of time my next smallest would either be the node which is being pointed by head 1, or it will be the node which is being pointed by head 2, like how it was in arrays. So here the smallest of them is 1, so I can create a new node having 1 in it, and then I'll move this pointer. Now again the smallest of these two is this, so I'll create a new node having 3 in it and connect this to this, and then I'll move this thing. So this is the way in which, you know, you compare, create a new node and move the corresponding node. Compare, create a new node and move the corresponding node. So this way you can get your job done, right? So how much will be the time and space complexity of this approach? The sizes of the two linked lists are m and n respectively. So of course time should be m into n, and you are creating another linked list from scratch, so that will contain m plus n nodes. So again, like, it will take that much of time. But tell me one thing, is it possible to perform this merge without using extra space? Can I actually avoid that extra space, yes or no? Simply change pointers. Yes, very good. So how many of you feel like that I can simply change the pointers and get my job done? See guys, the intention over here is something like this. I'm not going to talk about this approach because this must be clear to all. So just think of it in this manner. I know for sure that whatever my output will be, in that this 1 will be kind of pointing to this 3. So can't I simply do that by changing the next pointer of this 1 from here to here? I can do that, right? So that is all that I am trying to say, that instead of, you know, creating a new node just because after 1 you have 5, you are creating a new node, you can make this 3 and 4 come after this 5 without even creating a new node. And how? Just by simply changing this pointer. So now you can make the next of this point to this, right? And then similarly, you know that this 4 has to point to this 5, so you can make the next of this point to this, and similarly next of this 15 point to this, and next of this 19 point to this. And let's say if there were many other nodes, 27, 29, 30, and let's say this was over, then you can immediately stop here. So if you manipulate with the connections in this manner, then your job will be very easily done. Okay, so how do you exactly do that? Let us learn how do I exactly get this thing done. So let's say there is a linked list that has 1, 2, 3, and then 6, and then 11, and then so on and on and on. And let's say there is another linked list that has 7, and then 12, and then 12, 15, 21, and then something. Okay, then what can happen here is that, so let's say this pointer is P1 and then this pointer is P2. So see, many things can happen. First thing is that the P1 value happens to be smaller than, or let me call equals to, P2 value. If this is the case, then I know for sure that there will be some portion from P1 till some part which has to come before this P2. I know that thing for sure, right? One more thing. Is it wise to do something like this? The moment I see P1 val is smaller than equals to P2 val, is it wise to simply disconnect this and connect this? No, this is not wise to do. Why? Because of the original reason that I said. And what was that reason? Just because 1 is smaller than 2, 1 is smaller than 7, it doesn't mean that only 1 will come before 7. Many things starting from 1 can come before this 7. So what I have to do is, the moment I see that P1 pointer is smaller than P2 pointer, you can just keep moving this pointer on and on and on and on and on, as long as you do not get a value which is strictly greater than this value. You can do that, yeah, or null, because at times it can happen that, let's say this was the last node, so it can become null also. I mean, P1 can become null also in this case. So what usually you will do is something like this, that you will keep moving this pointer on and on as long as the value being pointed by P1 doesn't become strictly greater than this 7. So keeping that in mind, your P1 will end up over here. And now, what do you want to connect to P2? Do you want P1 to connect to P2, or do you want this 6 to connect to P2? What do you want? You want that 6 to connect to P2, right? So how do you keep track of that? Is there an easy way to keep track of that? I think very easy way to do that, right? I can have a prev pointer, and whenever my P1 moves, before moving my P1, I'll capture the old value of P1 in a variable called prev. So this way what would happen, when you land here, your prev1, I'm going to call it prev1, your prev1 is actually here. Now using this prev1, you can simply make it point to this value. So now whatever has happened is right. Now let us try to understand one more thing. Let's say you had something like 7, 9, 10, 15 and so on. So now the same thing that had happened for P1 and P2 over here is now happening for P2 and P1 over here. Don't you think so? I mean, what is the situation over here? What is the situation over here? The situation over here is that now your P1 value is greater than P2 value. This P1 value is greater than P2 value. So if your P1 value is greater than P2 value, again does it make sense to simply disconnect this and connect this? Does this action make sense? Yes or no? No, this does not make sense, because just like the previous case, I can have a big portion, a really big portion that starts from 7 and ends somewhere which should come before this. So now again I'll do the same thing. What I'll do, just like prev1, I'll have something called as prev2, and The moment my P2 is moving in one direction, before moving it, I'll capture its old value in prev2. So can you tell me till what time will you move this P2? You will keep moving this P2 as long as P2's value is strictly smaller than or equal to this value. Till that time you will keep on moving this P2, right? So guys, does that make sense to all? Yes or no? Yeah. So can you tell me on which node P2 will stop? On which node P2 will stop? Yes, P2 will stop on 15. And when P2 has stopped on 15, where will this prev2 be? Can I say this prev2 will be here? The answer is yes. So now I can connect this prev2 with this 11. And now again the same thing will happen at the level of P1 and P2, because now this condition is true. So now again I'll keep moving this along with prev1 as long as I cannot connect something over here with this thing. Yeah, so what is happening over here is that instead of having to create new nodes, I can simply tamper with the links and get my job done. So this is one very good thing about dynamic data structures, that if even if your space or your size is not fixed and such kind of dynamic memory allocation is there, then you can use the same memory to rearrange it however you want to do. Tell me one more thing over here. Let's say this 10 was the last pointer. Let's say this linked list was just from here to here. So at this point of time, what would have been the value of P2? It would have become null. Very good. Can I say that the moment P2 becomes null, or the moment P1 becomes null? Okay, let's first do it for P2 becomes null. The moment P2 becomes null, can I say that, hey, now I need not do anything? I can say that, right? Because now there are no nodes left in this part, and also this is correctly connected to this, and this part is already sorted. So I need not do anything else over here. So an important thing to understand over here is that in case of arrays, when one array had certain elements left, I needed to do some processing. Yes or no? I needed to copy those elements one by one and place them into the output array. But here you do not have to do that. Now again, when you code for this approach, what you have to be very careful about is the edge conditions and dealing with pointers, NPs and everything. Tell me, when will you terminate your algorithm? So you have P1 and you have P2. When will you want to terminate your algorithm? Can I say that the moment I see that P1 or P2, if either of P1 or P2 becomes null, that means I can simply stop. Yes or no? Yeah, because I showed you what happened when P2 was null. The same thing will happen when P1 has also become null. It can happen, right? It can very well happen. Let's say there was a 12 over here, and then there was, let's say, nothing over here. And then the remaining part over here, let's say it was 15, 16, 17, 18. So this P1 would become null, and this prev1 would be here, and now you'll connect this prev1 with this. And then once your P1 is null, you can say that, hey, your job is done. So how do I write the code for this approach? Let's say I want to merge, and after merge I need to return the head pointer, right? So okay, can I say that the head of the resultant list will either be H1 or H2? Can I say this with guarantee? I can say that, right? One of them. But which of them? Which of them? Tell me. Because before you tamper with these links, a great idea is to first decide that what will be overall head. Can I say it will be minimum of these two? Whichever is minimum, that would be the head, right? But there is an edge case over here. What if both of them are equal? Can it happen or not that H1 data and H2 data both are equal, right? So in that case, what would you want to do? So in that case, you have to just be consistent, because in that case your head can be this also and your head can be this also. Does it really matter? It doesn't matter. Let's say you have 1, 1, 2, 3 and you have 1, 4. 5. So your head can be this also. When your head is this, then the expectation is to convert this thing into something like this, where this is connected to this, and then now this is connected to this, and then this and then this 3 is connected to this. So with this expectation, you can have this as your overall head, but you can also consider this thing as your head. Okay, so let's say you have 1 1 2 3 1 4 5. You can also consider this thing as your head, but when you do that, then the connections will be a bit different, where your 1 will now point to this, and now this 3 will point to this. So just the connections have changed, but the answer, even if you had had this head, it would have been correct, and even if you have this head, it would be correct. But the only thing to be kept in mind is that when you let's say the values are equal and you consider this thing as your head, then by mistake also you should not perform this connection. You should definitely go through this route, because if your head is this and you go through this route, then that will be a wrong answer, because then you say that this is your head, but in reality this is your head. So while implementing, you have to be very, very careful about this thing. If you are not careful about this thing, then you will get a wrong answer. So let's see how I am going to implement this. So what can be the edge conditions with respect to L1 and L2? So if L1 is null, what should I do? I'm supposed to merge two linked lists, out of which one of them is null. What will you do in this case? Yes, then simply return the head of L2, because that would be the only list and the head of that would be the answer. Similarly, if L2 is null, what should I do? If L2 is null, I should return L1. Now, I do not need to write a separate case where both are null. Do I really need to write a separate case where both are null? No, because that would automatically get handled by either of these two conditions. Just use some brain, it will, right? Okay, otherwise what I should do is, I should declare a head and I can initialize it to, let's say, null. And now depending on the condition, so let's say if I see that L1 val is smaller than equal to L2 val. If L1 val is smaller than equals to L2 val, I am going to say that, hey, my head is L1, else my head is L2. So this is the place where I have just decided my I just have decided my actual head. Now next, what I should do? Next, my logic should be written in this way: while L1 is not null and L2 is also not null, till that time I should do one thing. Now tell me, if there was a case where this equality came into picture, and you decided that, hey, this should be your head, right? Because in case of equality, you go ahead with L1. So is it safe to first iterate over list 1 when there is equality, or is it safe to first iterate over list 2? On which list would you want to iterate when the head of both of them were equal? Yeah, you must iterate on list 1, because if you iterate on list 2, what would happen is that this thing is your actual head, but you made this thing point to this, right? So all that I am saying is that logic of, moving P1 as long as you do not get a value greater than this should first be written for list 1, and then it should be written for list 2, because you have given preference to list 1 to become the head in case of equality. So that is the only thing that I have to be aware of. Now, how is the code going to look like? So while I'll keep seeing that L1 value is smaller than equals to L2 value. Let's take a case over here. While L1 value is smaller than L2 value, I'll keep moving this on and on and on and on, right? But should I have a check before this? Because in this while loop, it can happen that your L1 reaches null. So while my L1 is not null and this thing is true, till that time I'll keep doing something. Okay, and let us have a previous pointer also. I can get my job done with one previous pointer also. I don't need previous one and previous two. Okay, so as long as this condition is true, what I should do is previous should capture the current L1 and L1 should be modified. L1 next. This is how I would go on and on. Okay, after this what would you want to do? What are the things that can happen here? So now at this point your prev would be somewhere here, because your prev is now somewhere here, so you can easily connect this prev to this L2. Now the way to do that should be, once this while loop is over, all that you can do is prev next equals to L2. Okay, do I have to worry about this prev being null? Will this prev be null at this point of time? Can it happen that this prev is null? It will not be, right? Because the reason this loop ran was because both of them were non-null. And because both of them were non-null, if let's say this was non-null and if this condition was true, then it would never ever happen. It would never ever happen that previous is pointing to a null pointer. But you should think of one more case where you might end up getting null pointer exception despite this thing, and that is very easy to be thought of. Let me tell you, if you have something like 7, 9, 11 and you have something like 1, 2, let's say this is the case. So here your head would be this because of this condition. Now when you enter this loop, will this thing run? You of course initialize your previous to null over here. Tell me, will this thing run? Corresponding to this input, will this thing run? Yes or no? It will not run, right? Why it will not run? Because, I mean, here your L1 is this and your L2 is this, and your L1 value is not following in this category. So the second part where the L2 changes, that part will run. So you have to be careful about that, right? This was a very important point, and you have to consistently have an eye over that. So I will write that only if my prev is not null, then I will say that hey, now my prev next should become equals to L2. Cool. So this is one check that I had. Now tell me one more thing over here. I can have a logic to terminate here only. Let's say it so happened that after this loop ran, my L1 became null. So if my L1 became null and I have connected prev with L2, then I can simply check for that condition and disconnect here itself. Yes or no? I can do that. So if I see if not of L1, I will break. Although it doesn't make much of sense. It will get broken by this also. But the reason I am writing this logic is it will make my life easier to write the next logic. So my next logic will be where I move this thing. So for that I'll have while my L2 is not null and L2 value is smaller than equals to L1 value. So as long as this is the case, what I'll do is prev will be L2 and L2 will be L2 next. Okay. And now again, because if this thing has run, then what would happen is after this I can have prev next equals to L1. And now again this same kind of logic you can have over here at the level of L2. If L2 has become null, break. And finally you can return the head. The last logic will be to return head. You will realize that you do not need this if condition to come over here. You do not actually need that if condition. Why you do not need that if condition is because one thing is for sure, that if let's say this code has run, if this code has run, then definitely prev will not be null. Okay, definitely prev will not be null. And even if this code has not run, then also prev will not be null. Okay, so you can think about that. You can think about that on your own. So this is the overall logic. You can change some things over here if you feel that I have written this code in a very fast manner. If you see that you can improve certain things, you can reduce redundancy, simplify it further, you can do that. But this is the overall logic for getting this task completed.